Okay, hope you had some good opportunity to practice tabular integration with the application of the Lipit rule to help you make those good choices for you. We're going to build on that today, and we're going to move forward with using bounds and finding the value of that plus C that you add to the end of the tabular integration. But if you've got specific values, either values for your bounds or an initial condition, you'll be able to find that plus C values. So let's just quickly slide through our rules of thumb, okay? Tabular integration is great, but it only works in certain situations. So U substitution should always still be your first choice. If you can write it with parentheses, it's always a good idea to investigate whether or not the U substitution would be a good choice first, or if it can be written as a product. Only in the situations where you've tried those things, but you can't reduce it nicely, all right, things don't all simplify well, then you try tabular integration. And then we talked about the different rules for the Lipit test. So we have any kind of a logarithm would be your first choice, and an inverse trig would be your second choice. We haven't done any of those yet. That'll be coming on Wednesday. But we did look at polynomials or powers, the exponentials coming next as your next choice. And then trigs are always, so trig functions are always last in terms of priority, and we've been working with the PET options for tabular integration. And then the leftovers would be your DV part. All right, so let's take a look at using tabular integration, and then this problem has bounds on it, which means that we'll be able to go farther than we had before with the plus C. All right, but let's make our U choice first. So we're using the Lipit test. We're going to start with the P. So my U is going to be chosen for x squared. And so then I'll go to 2x, and I'll go to 2, and I'll go to 0. And then my other column of the table would be the dv part left over as the cosine of x over 2. And then my antiderivatives for that. So the antiderivative is sine of x over 2. And then the chain rule says I need to divide this by 1/2. But rather than dividing by 1/2, I would rather multiply by the reciprocal. So I'm going to get rid of that, and I am going to multiply by 2 instead. And then I'll do it again. Antiderivative, and multiply by 4. And then one more antiderivative, and I'll multiply by 8. Okay, now I'm ready to do my pairing. So I'm going to pair these two together. I'm going to pair the next two. Those will be with a minus sign. And then I'll pair the last two, which would be positive. Okay, so what do we end up with? We end up with our first pair, which would be 2x squared sine x over 2. And then plus, because of the double, we've got a double negative here. So plus 8, it looks like, x times the cosine of x over 2. And then minus 16 times the sine of x over 2. And then plus c. But now we can go farther because our bounds here were 0 and pi. Oh, shoot. You know what? This is a typo. This should be pi halves. Can you change that? Okay, pi halves. Now that's better. Okay, now we're ready to substitute in the upper bound and the lower bound. So this would be 2 times pi halves plugged in squared times the sine of pi halves over 2 plus 8 times pi halves times the cosine of pi over 2 minus 16 times the sine of pi over 2 over 2. plus c. And then we'll plug in all the zeros. So 2 times 0 squared times the sine of 0 over 2 plus 8 times 0 times the cosine of 0 over 2 minus 16 times the sine of 0 over 2 and minus c. Okay, our plus c and our minus c can reduce out here. We've got all the zeros. And then we have the sine of 0, so we have a bunch of 0 things here. We also could maybe write the sine of pi over 2 in a better way, and that would be the sine of pi fourths. So what I'm going to do right now is change all of these to pi over 4, which is a cleaner way of writing that. So sine of pi fourths, and pi fourths. Okay. So that's going to give me 2 times pi squared over 4, and then times the sine of pi fourths, which is rad 2 over 2. And then plus 8 times pi over 2 times the cosine of pi fourths, which is also rad 2 over 2. And then minus 16 times the sine of pi fourths, which is rad 2 over 2. So let's simplify anywhere that we can. So my 2's are going to reduce. My 2 and my 8 reduce to get 4. And then my 2 and my 4 reduce to leave me with 2. And this leaves me with 8. So my final answer would be pi squared rad 2 over 4 plus 2 pi rad 2 minus 8 rad 2. Now because these all have a rad 2 in common, I could factor out the rad 2, leaving me with pi squared over 4 plus 2 pi minus 8 also as an answer. So we were doing the same thing as we were doing yesterday. We're just adding the step of having bounds on the end and then plugging in the upper bound and the lower bound. So let's try another one. Find the area of the region enclosed by x times the sine of 2x in the x-axis on the interval 0 to pi. Anytime you're asked about area, always a good idea to take a look at the picture that this represents. So when we sketch this and we go from 0 to pi and we go from -1 to 1 like we should for sine, we get this graph that looks like this. So part of this area is above the x-axis and part of this area is below, which means we're going to have to separate our integral into two different pieces at where that intersection spot happens, which is pi over 2. So we got to be careful about, separating it into a positive and then a negative area. Okay, so we're going to have an integral. One integral is going to go from 0 to pi over 2. And we'll be doing x sine 2x dx. And then we've got pi halves to 0, or excuse me, to pi. And then we need the absolute value of x sine because it's below the x-axis. So we're going to have to consider that to make sure that we get it positive so that we can think about what the total area is. All right, so we're looking for the total area between the two. All right, but first let's do our tabular. So according to the Lippitt test, we have our polynomial. Okay, even though the power is 1, right? It's not a complex polynomial, but it's a polynomial nonetheless. And so my u choice would be x, and the derivative of x is 1, and the derivative of that is 0. And then everything else would be my dv. And we'll work on some antiderivatives. So the antiderivative of sine is negative cosine 2x divided by 2. And then the antiderivative of that is negative sine 2x, and then that would be divided by 4. So we'll pair them up together, and my second pair is going to be my negative pair. Okay, so what do we have so far? What's the result? So the result would be negative x cos 2x over 2. And then we'll have a minus a negative, so that would turn into a plus sine 2x over 4 plus c. But now we need our bounds, okay? And so we're gonna have to do bounds twice on this. So let's see, I've got negative x cos 2x over 2 plus sine 2x over 4 plus c. And the first time I do it, I'm going to go from 0 to pi over 2. We also are going to have an absolute value of negative x cos 2x over 2 plus the sine of 2x over 4 plus c absolute value. And this one goes from pi halves to pi. So how do we work with an absolute value? Well, remember, an absolute value takes things that are negative and makes them the opposite. And so if I want to take off these absolute value bars, which I do, I have to make the signs inside the opposite. So I have to change this negative to a positive and change that positive to a negative. So the result is going to be a negative here. All right, that's how you work with absolute values. Change the sign and only do that on the part that was below the x-axis. All right, so now we're ready to plug in, and we're going to get our total area. We're going to do the top area, the area above, and the area below. So negative pi over 2 times the cosine of 2 times pi over 2, all over 2, plus the sine of 2 times pi over 2, all over 4, plus c, and then minus negative 0 times the cosine of 2 times 0, all over 2, minus the sine of 0 over 4, minus c. All right, so my plus c and my minus c cancel out. The sine of 0 over 4 and 0 times the cosine of 0 over 4. And so all of this then on these two will reduce, and those two will reduce. So I'm going to have the cosine of pi, and I'm going to have the sine of pi to figure out here. The cosine of pi is negative 1. The sine of pi is 0. So that's going to take out this whole thing also. So wow, it really only left me with this. So negative pi over 2 times negative 1 over 2. So double negative makes a positive. So the answer to that is pi over 4. All right, let's do the second part. Okay, I'm going to plug in all of my upper bounds. So that's going to give me pi, the cosine of 2 pi all over 2, minus the sine of 2 pi over 4 plus c. And then minus, now I'm going to plug in pi halves. So pi halves times the cosine of 2 times pi halves over 2 plus, the sine of 2 times pi halves over 4 minus c. All right, minus plus c's minus c's cancel each other out. What else do I have? I have the reducing here. Okay, let's start at the back. The sine of pi is 0, so that knocks all of this out. The cosine of pi is -1. The sine of 2 pi is 0. And the cosine of 2 pi is +1. So I am left with this expression here, pi times 1 times half. And then I'm left with this expression minus pi halves times -1 times half. So I'm left with pi halves from the first yellow rectangle, and then plus, because of the double negative, pi fourths. So now I want to put that all together. Pi fourths plus, that's the original pi fourths here, plus pi halves plus another pi fourths. And so that's just going to give me my total. And my total turns out to be 4 pi over 4, or just pi. So the total area of all of this negative and positive area added together is pi. All right, another time we work with C is when we have something called the initial value problem. And that's where you have enough information so that you can figure out what the value of your plus C is going to be. So you're given a point in the form of x, y, and we're going to use that to solve for our C. So we're still going to do our tabular integration. We'll have our plus C on the end, but rather than plugging in bounds, we're going to be plugging in a point so that we can figure out the value for C. Okay, so this is an initial value problem. We have a derivative problem, and then we have an initial condition here where we have values for 0 and 2. And we want to solve this with tabular integration. So we have our P here, our P piece. And so then we'll say, all right, my U will be 2x minus 1. So the derivative of that is 2, and the derivative of that is 0, which leaves the dv piece to be just cos x. So the antiderivative of that is plain sine x, and the antiderivative of that is negative cos x. So let's pair up. We'll pair here, and we will pair the second time, which would be a negative. So my answer is, and the answer should start with y equals a pair of 2x minus 1 paired with sine of x, and then minus a negative, so plus cos x plus c. Now we're going to use the initial values. So y equals 2 and x is 0. So my y equals 2 will go in for y. And my x is 0 is going to go in all the places where we have x. So a bunch of those are all going to be 0. So I'm going to have 2 equals 2 times 0 minus 1 times the sine of 0 plus the cos of 0 plus c. So 2 times 0 is 0. Sine of 0 is also 0, so all this is knocked out. But the cosine of 0 is not. The cosine of 0 is 1. So that helps me to figure out that C has a different value. So I'm looking at 2 equals 1 plus C. So then C, of course, must be equal to 1. So my final answer, now that we know what this C value is right here, my final answer would be written this way. Y equals 2x minus 1 times the sine of x plus the cosine of x plus the constant 1. And that is the solution to this differential equation here. Okay, let's try one more of those. Here's another initial value problem. So it's the derivative, whose answer will start with y equals. But we have this initial condition value here. All right, so let's pick our limit, and we've got a p for polynomial here, and we've got an e for an exponential. So my polynomial is chosen to be 3x squared. Derivative on that would be 6x. Derivative on that would be 6. Derivative on that would be 0. And then e to the 3x, and we'll work on finding the antiderivatives of that. So this will be e to the 3x divided by 3. But I'm going to write that as multiplied by 1/3 instead. Okay, so whoops. There we go, erase that. And I'm going to put 1/3 in front. And then another e to the 3x, and then divide by 3 again, so that will be 1/9. And then one more e to the 3x divided by 3 again, which will be 1/27. Okay, let's work on our pairs. So we'll pair these up. And this one would be subtraction. Okay, when we do our first pair, the 3 is going to reduce with the 1/3. So I'll be left with x squared e to the 3x. My next pair will be minus, and the 6 will reduce with the 9, giving me a 2/3 x e to the 3x. And my last pair, my 6 will reduce with my 27, giving me a 2/9 e to the 3x, and then a plus c. So now we've got our initial conditions. We know that y is -1 when x is 0. So let's plug all those in. So -1 for y, 0 for x. Oops, I forgot to plug a 0 in there. Times 0. Minus 2/3 times 0 times e to the 3 times 0. Plus 2/9 times e to the 3 times 0 plus c. So 0 squared times e to the 3 is a 0. Minus 2/3 times that, that's a 0. Here, e to the 0 is 1. So that means this whole term is 1. So now we've got -1 equals 2/9 times 1 plus c. So we should be able to figure out what c is by subtracting 2/9 from both sides. So c is -1 minus 2/9. That's -11/9. So my overall answer would start with y equals, it would be x squared e to the 3x minus 2/3 x e to the 3x plus 2/9 e to the 3x, and then minus the constant 11/9. Or you might see this written as the GCF of e to the 3x factored out front, and then left with x squared minus 2/3 x plus 2/9. But the 11/9 is still the c value at the end, so you might see it written that way as well. And that's your final answer for that differential equation. So remember, a differential equation is something that starts as either a dy dx, and so its solution would be y equals, or maybe starts as an integral. And one of the techniques we have is this tabular integration system. All right, so we'll see you on Wednesday, and then we'll talk about what we do with logarithms and inverse trig. All right, see you then.